These are the notes for AP Calculus on the topics of the direct comparison test and the limit comparison test. So, both of these tests require that you compare it to a similar or simpler series. So when you're going to use these tests, you always use them in conjunction with another test that, that would work with the simpler or similar series. So usually on these, if you can use the direct comparison test, that tends to be the easier of the two, but it doesn't always apply. So when it doesn't apply, then you can fall back on the limit comparison test. So it says determine whether the series converges or diverges and specify what tests or tests are used. So one way to figure out what to compare it to is to think about, well, if you substitute infinity into your formula, here's your a sub n formula here. What's not going to matter? So the insignificant part here, this plus 2n is going to be negligibly smaller than the n to the fourth. So that gives us a clue as what to compare it to. Let's compare it to the series from n equals 1 to infinity of 5n squared over n to the fourth. And then you can simplify this. Notice, just like with integrals, you can pull the constant coefficient on the outside. And then this simplifies inside there to just be 1 over n squared. So sometimes you can tell which of those larger of the two. In order to use the direct comparison test, you have to be able to tell which one's going to always be larger. If you can't tell that, then you have to use the limit comparison test. Here, with this one term added on the denominator, since it's making the denominator larger, that's going to actually make this one smaller. So you can say this one's always smaller than. And then just to be consistent with the formula here, let's always label the smaller of the two as a sub n for the formula, and the larger of the two b sub n. So it could be either way, depending on what you're comparing it to. So this would be our smaller one, and this is the larger one here. So now we can see this 1 over n squared. The simple one, we can see if it's a p-series one, where p is the exponent right there, p is equal to 2. And remember the p-series test, since this one is greater than 1, that tells you it converges. Versus if it was less than or equal to 1, it would diverge. Okay. So, if this one converges, that means it approaches a specific number. And this one here, our original one, is always smaller than it. So there's no way this can go to infinity. It has to also be smaller, has to be smaller than one that converges, so this is where you can use the direct comparison test. If this had said diverges, then it would be inconclusive with the direct comparison test. We wouldn't know for sure just because it's smaller if this was infinity. If it was a diverging one, it could converge, it could diverge. So in order for this to work, when it's smaller than the one you're comparing to, it has to be the one you're comparing to converging to use the direct comparison test. So we can say it converges by the direct comparison test. And you always have to use another test. In this case, we use the p-series test. All right, let's take a look at the next one. The next one's one of the trickier ones. I've seen one similar to this on the previous AP test here. This one's square root of n, natural log of n. The toughest thing to compare it to here, the toughest part is figuring out what to compare it to, I should say. And there might be other ways to go about it, but I think probably the easiest way is just think about, well, if we're going to use the integral test on this and set u equal to natural log of n, the derivative would be 1 over n, and that would cancel out this if it had just been n instead of square root of n. So So to compare it to something similar to this, with just n instead of square root of n. So those are pretty similar there. And since this one, when you start substituting 2, square root of 2 is smaller than 2 on the denominator. So this one has a larger denominator, making this one smaller. So we can say this one's always larger than. And then using the integral test, remember we rewrite it as the integral, and your lower limit here is 2 in this case, upper limit infinity of our formula. So this one, in this case, the smaller one here, this is our b sub n, sorry, small a sub n, I should say. And the larger one here is our a sub n. That's our b sub n, I should say. Sorry, I just getting that spaced up there. All right, so with the integral test, 1 over n natural log of n, or if you don't like using n, you could also just pick a different variable, use like x. And then, like I said, to integrate this is going to require u substitution, setting u equal to natural log of n, because then the derivative of that, u dn, is just 1 over n, and then when you cross multiply, the n times 1, you get dn equals n times du. So that can replace the dn. But since it's a definite integral, remember we also need to convert the lower and upper limits. So you plug in infinity, natural log of infinity, that is infinite, but I'm just going to leave it as natural log of infinity. Occasionally it might matter that it's natural log of infinity rather than just infinity. And then when you substitute 2, you get natural log of 2, which doesn't simplify at all. So you have 1 over n times u, just replace the natural log of u, and then that dn is the same as n du. So then you can see the n's reduce out. And then we're just left with the integral sum that we can integrate. 1 over u gives you natural log absolute value of u, valued from natural log of 2 to natural log of infinity. And both of these are already positive values, so the absolute value doesn't have any effect there. So natural log, the natural log of infinity, minus the natural log of the natural log of 2. Well, natural log of infinity, even though it grows really slowly, does go to infinity, and then the natural log of infinity again. So this part's infinite, even this part's not. So because of this infinite part, this we know diverges by the integral test. And remember, the integral test says if the integral diverges, so does the series, that is in the same format. So let's think about this. This time we know this one diverges, and it's the smaller of the two, so it goes to infinity. So if this one's the smaller of the two, and this one's larger than it, there's no way this can converge. It has to also diverge, head off to infinity, because it's larger than it. So we can say this one diverges by the direct comparison test. And we also use the integral test. Again, if this integral had given us a specific number and then told us that the series converges, then we wouldn't be able to use the direct comparison test, because if this one had converged and this one's larger than it, then they also could converge, or it could go to infinity and diverge. So we wouldn't know. We'd have to use the limit comparison test. So direct comparison tends to be a little easier if you can use it. So let's take a look at this one here. So we've got this plus n on the denominator. That's not going to matter when we go to infinity, so we can compare this to n equals 1, 4, which is 4n squared over n cubed. again, simplify that. Sorry, whoops, I put the 4 in the wrong place. So that's infinity on the top there. Otherwise, it wouldn't be an infinite series. I can pull this 4 on the outside, just so we do it in close constant coefficient. And then what we're left with when we simplify is just 1 over n. So again, this plus n on the denominator means it's the denominator is larger, means it's always smaller than. So this would be our smaller one, a sub n. This would be the larger one, b sub n. And this one also, notice fits the p series. You can see right there, p would equal 1. But this time, since that's less than or equal to 1, in this case it's equal to, by the p series test, that tells us this diverges. Okay. And that means basically it's heading to infinite. Okay? It diverges. And this one's smaller than. Well, this one could also be infinite too, smaller than, just not grow quite as fast, or it can converge to the splitting divide. So if it's smaller than this one, and this one diverges, you can't use a direct comparison test. So here we have to fall back on a limit comparison test. So with a limit comparison test, you find the limit as n approaches infinity. And it looks similar to the ratio test, except you don't substitute in n plus 1. You just use the 2, you find the ratio of the 2 you're comparing it to. So the original one, you can put on the numerator, and the one you're comparing it to on the denominator, and divide them. And the key is if you get a limit that is positive, greater than 0, but not infinity, so if it's positive but finite, then you know they both converge or both diverge. They do the same thing. All right, so let's see how that works on this one. So our original one we had was, this a sub n was 4n squared over n cubed plus n. And then divided by the one we're comparing it to. This 4 is still part of it, even though we pulled it out in front, so it would be 4 over n. And then, of course, you can simplify it. You can do this in your first step if you want to save yourself a step like we do in the ratio test. The same as 4n squared over n cubed plus n times reciprocal n over 4. Then you can see the 4's reduce out, and we get n cubed times the n squared there, n cubed over n cubed plus n. And then when you substitute infinity, on the numerator we've got infinity cubed, and what matters on the denominator is infinity cubed with plus n, and n is negligible. So those reduce out, and we just get 1. And since that's greater than 0 and not infinity, that means the limit comparison test can be used, and they will do the same thing. Since this one we compare it to diverges, this one will also. So this one we can say it diverges by the limit comparison test. And we also use the p-series test. All right, let's take a look at one more here. All right, so on this one, we're subtracting n. That's a little trickier on the denominator there. So you may be able to tell whether this one's always larger or always smaller, but there are some problems where you can't tell at all. There's like too many terms, like one of the ones I had on the previous video there. So if you can't tell at all, rather than trying to figure out if it's smaller than or larger than, you can just decide you're just going to compare it to one. And then just go directly to the limit comparison test. So you don't have to start with a direct comparison test if you don't want to. It just sometimes is a little easier than the limit comparison test. So if we have 3 to the n minus n, and remember exponential ones are larger than the polynomial ones, even if this had been n to the 10th. So what we can compare it to is 1 over 3 to the n. And then you can see this one, not p-series because the exponent is the variable here. Notice this one, the n is up there, and if we find the first 3 terms, this looks geometric here to me. If you find the first term, substitute the starting number 1. First term would be 1 over 3. The second term, 1 over 3 squared when you plug in 2, 1/9. The third term, 1 over 3 to the third, 27. So you can see being multiplied by 1/3 is our common ratio. And remember the geometric series test, if that common ratio is between -1 and 1, which it is here, that tells you it converges. If it's not, the common ratio is not between -1 and 1, then it diverges. So let's use the limit comparison test. This would be the limit as n approaches infinity. And then we start with our original one, 1 over 3 to the n minus n. And then dividing by this one is the same as multiplying by the reciprocal. 3 to the n over 1. And then when you substitute infinity in here, there's nothing you can simplify here. You'd have 3 to the infinity. You can see the minus n is going to be negligible, so 3 to the infinity. So it's a common thing. You don't always get 1 with a limit comparison test, but it's a very common thing to get a limit comparison test. And again, since that is something greater than 0 and not infinity, not infinite, then we can't use the limit comparison test, and these will do the same things. So this one converges, so will our original one. So we can say this converges by the limit comparison test. And we also use the geometric series test. And that concludes notes for AP Calculus on the topics of the direct comparison test and the limit comparison test. Continued.